Light is a form of electromagnetic radiation. At some wavelengths, it appears as visible light. At others, it takes the form of radiation we cannot see, such as ultraviolet, infrared, and X-rays. X-rays have very short wavelengths that, unlike visible light, are able to pass right through most tissues in the human body. Since bones contain calcium, a denser material than most other tissues, they are able to stop some of the X-rays and can thus form a shadow. If you place your hand in front of a flashlight, it will cast a shadow on the wall behind it. In a similar manner, X-rays directed at the body produce shadows on the opposite side that can be registered on film or on a digital sensor, so that bones are clearly visible while soft tissues, such as muscle, are shadowy. As a result, the two-dimensional images formed by the X-rays are quite useful in revealing structures within the body and can easily display fractures in bones. A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing. CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient. There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments. A PET scan creates 3D images of the body. It does this by using radioactive tracers, which are usually administered to a patient through intravenous injection. The tracers are made up of carrier molecules that are tightly bonded to a radioactive atom called an isotope. The carrier molecule can interact with or bind to specific proteins or sugars in the body. The carrier molecule that will be used depends on what the doctor is looking for. If she suspects cancer or is monitoring a known cancer's growth, she may use FDG, a modified form of glucose, which gets absorbed by tissues. When tissues absorb a lot of glucose, it may indicate a cancerous tumor. The radiation from the tracers poses little danger to the patient since they quickly pass out of the body. The isotope produces small particles called positrons, which interact with surrounding electrons. This interaction results in the complete annihilation of both particles, releasing two photons that speed off in opposite directions. The detectors in the PET scanner measure these photons and use this information to create an image of the distribution of FDG in the body. The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image. MRIs use protons, which are abundant in the human body. All protons spin, creating a small magnetic charge. When a strong magnetic field is introduced, as is the case in an MRI machine, the protons align with that field. The MRI technician then introduces a radio frequency pulse that disrupts the proton and forces it either into a 90-degree or 180-degree realignment with the static magnetic field. Since the radio frequency pulse pushed the proton against its nature, once this pulse is turned off, the protons realign with that magnetic field, releasing electromagnetic energy along the way. The MRI is able to detect this energy and is able to differentiate various tissues based on how quickly they release energy after the pulse is turned off.